Welcome back. I'm Dave Barker-Plummer.
And I'm John Etchemendy.
In the previous video, we described the tools that we're going to be using in this course to help us to understand and explain the logical properties of propositions expressed in natural language.
Now, the first and foremost among those tools is the language of first-order logic, FOL, or FOL, as Dave pronounces it. In this first video, we'll start by learning FOL with the very simplest components of the language, expressions that we call atomic sentences. An atomic sentence is the smallest unit in the language that can be used to make a claim about the world. That is, it's the smallest unit that can be said to be either true or false.
Here are some example English sentences, which we will aim to express using atomic sentences in FOL. Socrates is a man. 2 is an odd number. Quinn is older than Max. And the Eiffel Tower is taller than the Golden Gate Bridge. Now, just like real atoms, atomic sentences have component parts. In particular, we want you to notice that these sentences all involve names, which are used in English to pick out objects in the world. The first 2 of these sentences ascribe properties to a single object. For example, Socrates is a man is a sentence that says of the object named by the word Socrates that that person is a man. And 2 is an odd number says of the number 2 that it's odd. The second 2 sentences assert that there's some kind of relationship between 2 objects. So Quinn is older than Max invites us to find the object named Quinn, the object named Max, and to see whether one is older than the other.
So let's start by thinking about names in natural language and in FOL. FOL contains a number of items which we call individual constants, which function in FOL much the same way that names work in natural language. In fact, we'll sometimes just call them names. But it turns out that there are some subtleties about the way names work in natural languages, which we'll need to clarify in order to explain the behavior of FOL's individual constants. So the first thing that we need to know is how to write individual constants in the language FOL. We write constants with a sequence of characters which begin with a lowercase letter, and which do not include the space character. So here are some examples. Socrates, we would write just like we do in English, except with a lowercase s. Max, Quinn, 2, we'll get back to that. Now Eiffel Tower, since it has 2 words, we have to make it a single sequence of characters, so we write it with a lowercase e and t, and we put an underline in between them. Similarly with Golden Gate Bridge. So you'll notice that this list of constant symbols is pretty much exactly what you would expect. We've just lowercased the letters and then substituted the underline character for any space to accommodate the rule that constant symbols can't contain spaces.
And you'll notice that we included the number 2 as a constant symbol in this list of examples. Now, all rules have exceptions, including this one. And we're making an exception for the number 2 and allowing it not to start with the lowercase letters. And we'll write all of the other numbers conventionally too. Mathematicians allow these numerals to appear in their arguments, and since there are more mathematicians than logicians, we just do as we're told on this one.
Now, one of the ways in which sentences in FOL are an idealization, a model of sentences in natural language, is that we want them to be completely unambiguous. When we're looking at a sentence in FOL, we need to be completely clear about what it says so that we can be completely clear about whether it is true or false in a particular circumstance. This means that we have to stipulate that every individual constant names, the technical term is denotes or refers to, a single individual or object in the world.
Now, this is an idealization of natural language, since the name Dave can be used to refer to many different people in the world. It turns out that there are about 84,058 Daves in the US alone. And do you want to guess how many Johns?
I guess more.
Yeah, there's 5,206,860 of you in the US alone.
You're really smart.
John is the second most popular name in the US, after James, in case you care.
I didn't know that.
So how on earth do we ever use the name John in a factual English sentence? Think, for example, of the sentence, John is a professor at Stanford. There are surely some people whose name is John for whom this is a true statement. and there are many more for whom it's not.
The answer, of course, is that when we use a sentence like this in English, we typically are in some particular context where it's clear which of the 8 million Johns that we're talking about. And so when we use the sentence, given the context, we can judge whether the sentence is true or not. We can't rely on such ideas of context when we're evaluating sentences in FOL, and so we simply say at the beginning of the conversation, so to speak, exactly which object we're referring to when we use the name John or Dave. And then sentences of FOL that are about John or Dave are perfectly unambiguous.
Of course, in a different conversation or in a different context, we may make a different stipulation and use the name John to refer to somebody else. Then the sentences that we use will be assessed relative to that new object. The important rule here is that in FOL, a name must refer to one and only one object. We've discussed that requirement that a name refers to only one object, but what about the requirement that a name must refer to some object, some actual object?
Well, again, this is an idealization of the way names behave in natural language. In English, for example, we can use sentences like Pegasus is a flying horse, or Santa owns flying reindeer, even though we know that Pegasus and Santa don't exist.
John, you can't say that on TV. There may be children listening.
I was just kidding. So anyway, there are plenty of names in natural language that don't refer to anything. In FOL, we require that every name refer to an existing object. If we use the name Santa or Pegasus in an FOL sentence, then there has to be some object that we're talking about.
Now, the fact that a name refers to one and only one object does not mean that every object has only one name. In natural language, objects can have more than one name. Think, for example, of Superman and Clark Kent, Mark Twain and Samuel Clemens, Jekyll and Hyde. Some objects even have more than two names. For example, Marshall Mathers, Slim Shady and Eminem, 3 names for the same person.
So this is a feature of natural language that we will not idealize when designing our language FOL. We allow an object to have multiple names. After all, this doesn't affect the ambiguity of sentences involving these names. Whichever name we use for a given object will unambiguously pick out an object in the world, and so the sentences in which it appears will be unambiguous.
And finally, of course, not every object has a name. This table doesn't have a name, and none of the air molecules in this room have names, at least as far as I know.
Sam.
In fact, having a name is a pretty rare thing in the world. The pen that John is holding doesn't have a name. It doesn't mean we can't talk about it, either in English or in FOL, but it will require a different mechanism than the use of a name in English. We say things like this pen. But we can even introduce a name for the pen. Henceforth, you pen, your name is Nigel. And now I can say things like, John is holding Nigel.
Here are these rules summarized. We'll say, first of all, in FOL, we assume that every individual constant refers to exactly one object. Some objects are referred to by more than one constant, and some objects are referred to by no constant symbols at all. Those are the objects that don't have names in the language. Now, as you can see, even an investigation of the simplest parts of natural language can require us to make explicit facts about the way languages work. These are facts we certainly knew, but which we may not have been able to articulate or never thought of articulating without thinking this way. And this is a good example of how studying FOL can help us to clarify our understanding of natural language.